Today I'd like to talk a little bit about system modeling, and I've reworked this lecture quite significantly over the years to cut down on some of the detail, but there's still a lot of detail. The previous one used to be 84 slides. I've got it down to roughly 44. It's still a bit of a weighty topic, and most recently I brought it in line with the 10th edition, so the images are now much clearer for you to see. Let's get started with system modeling. And the definition is the process of developing abstract models of a system, with each model presenting a different view of the perspective of the entire system. So it's now come to mean representing a system with some type of graphical notation, which is now almost always based on notions and notations in UML or Unified Modeling Language. These models help us to understand the functionality of the system, and they're often used during the requirements phase to clarify what the system will do, and also can be used to explain the system to different stakeholders. The little quote from George Box is from the Journal of the American Statistical Association entitled Science and Statistics, and expanding on it, since all models are wrong, the scientist cannot obtain a correct one by excessive elaboration. On the contrary, following William of Ockham, he should seek an economical description of natural phenomena. Just as the ability to devise simple but provocative or evocative models is the signature of the great scientist, so over-elaboration and over-parametrization is often the mark of mediocrity. By the way, Occam's razor states that assumptions should not be multiplied beyond their necessity, or in lay person's terms, the simplest explanation is usually the one that's most correct. Anyway, models are useful for having discussions with clients and product owners about proposed systems, and for eventually documenting how the system will work. So let's take a look at UML, or Unified Modeling Language. And there are about 13 different types of models in Unified Modeling Language, but most practitioners focus on just 5 of them: activity diagrams, use case diagrams, sequence diagrams, class diagrams, and state diagrams. And UML was first published in 1997 by Rumbaugh, Jacobson, and Booch. And the current release, 2.5, is from 2015. It's not a method or a process, it's a language. And the scope of UML is intentionally limited to a language. The building blocks are things, relationships, and diagrams. And you'll see a lot of different models in this presentation. Some of them are UML, while some are particular to Somerville or from my own experience. Activity diagrams show the activities involved in a process or data processing. Use case diagrams show the interactions between the system and its environment. Sequence diagrams show the interaction between the actors and the system and system components. And class diagrams show the object classes in the system and the association between these classes. Lastly, state diagrams show how the system reacts to internal and external events. There are also business process models, and I'll probably talk a little bit about those as well. By the way, the picture here, I once took a class from Rumbaugh, one of the inventors of UML. Ended up spending the evenings with him eating tacos and drinking beer. They were good times, and he was probably the coolest person that was actually there, although I liked all the instructors, but Rumbaugh was a cool guy. Barry Boehm is the one pictured to my immediate right, and he was the inventor of the spiral model. If you remember back to the different types of models that we saw in earlier presentation. So we'll start off with context models, and context models help to show how the system and its boundaries interact with other systems. It doesn't show how the systems interact or if they interact per se, but it shows the boundary between the system and the other systems. And this is not a value-free judgment. So when the authors say that it's not a value-free judgment, it means that organizational politics can play a large role in which systems interact with one another. For example, if you wanted to create a system that would push data to Laulima or a banner here at the University of Hawaii, you might have a sizable fight on your hands. Heck, even pulling data from different sources at the university, requires quite a few permissions and more than a bit of paperwork. And there are also process models that show how the process activities work for the system. These typically show actors in the business process, and they are more encompassing since the activities can take place offline or between people. For example, if you have an inventory management system, the process model could indicate that a worker picks the parts from a warehouse location as an activity. That's not something that happens inside the computer system, but something that happens as part of the process. So let's take a look at an example of a context model. This is figure 5.1 from page 128 of the 10th edition. Notice it doesn't say how the mental health care patient systems specifically interacts with these other systems. It just says there's going to be a connection with these other systems at some point in time during the development. So at some point in time, we're going to have to hook into the admissions system. At some point in time, we're going to need to hook into the management reporting system. And so it doesn't say exactly how that's done, but it says that it will be done. Here's another example process model, and again, this is figure 5.2 on page 129 of the 10th edition, and it deals with the process for involuntary detention of a mental health patient. This can be done when a patient suffering from a mental health condition represents a danger to themselves or to others, most often to themselves. Parts of this diagram, the filled circle indicates the start of the process, that confirms the detention decision. That's shown in around a rectangle, which is an activity. The diamond represents a decision. So, is the person dangerous or not dangerous? If they're not dangerous, we admit them to the hospital. If they are dangerous, we find a secure place for them. A line with an arrow represents the flow of work, and text inside of guards. So, for example, that dangerous, not dangerous. Those represent guards. So the text in the brackets are guards, and they are the conditions that indicate whether we should follow that arrow or not. And a black bar indicates activity coordination, things that take place in parallel. So informing the patient of their rights and recording the detention decision are things that take place in parallel. Another process model example, this was taken from some of the work that I did at Ford Motor Company, depicts the change control process for system changes. Shows the process flow, and it also has swim lanes that show who's responsible for each step. And so you can see the individual users at the top, the IT department, testers, and training who are all involved in this process. And it can show, it also shows who is responsible for each step. So the individual user is responsible for making a request to change the system. The user group, along with the IT department, are responsible for reviewing that request for change. In some ways, this is clearer than what you see in Somerville's model, even if the graphical design is probably not as crisp and clean. This was taken from back in the 90s. I like this one better because it says who performs what action. The one from Somerville doesn't say who performs the action. So interaction models, this is another class of model covered in Chapter 5, and basically all systems involve interaction of some kind. Somerville covers two types of interaction modeling: use case models and sequence diagrams. And you often see these models used in conjunction with one another. Use case models are used mostly to model interactions between the system and external actors or users. Sequence diagrams are used to model interactions between system components, although they can have external agents in them. So use cases, again, were developed to support requirement solicitation, and they're now incorporated into UML. Each use case represents a discrete task that involves some external interaction with the system. Actors in a use case may be people, or they can be other systems. Of course, you've seen use cases in previous lectures, but let's take a look at them in a bit more detail. So here's a use case along with the details, and this deals with our mental health system and the patient management system. So the actors are the medical receptionist and the patient record system, or PRS. Even though it's depicted as a human, it's a computer here. So a receptionist may transfer data from the mental health care patient management system to a general patient record database that is maintained by a health authority. This information transfer may either be updated personal information, for example, address, phone number, etc., or a summary of the patient's diagnosis and treatment. And then it indicates what data, the patient's personal information, or a treatment summary. Stimulus, a user command issued by the medical receptionist. the response is confirmation that the patient record system has been updated. And the receptionist needs to have the appropriate security permissions to access the patient information and the patient record system. Okay. And moving on to the next slide, you can also have composite use cases to show a number of different use cases. This is figure 5.5 on page 132 if you're keeping track in your own textbook. And it shows all the different ways the medical receptionist can interact with the mental health care system: registering patients, viewing patient info, contacting patient, transferring data, or unregistering the patient. Sequence diagrams are primarily used to model the interaction between actors and the objects in the system. They show the sequence of interactions that take place during a particular use case or use case instance. We read them from the top to the bottom. So we start out at the top and move all the way down to the bottom. The objects and actors are listed along the top, and the rectangles on the dotted line show the lifeline of the object. Lines with arrows show the flow through the system. So that seems rather abstract. Let's take a look at an example. Again, looking at our mental health care system, this is figure 5.6 on page 133 of the 10th edition. So here the medical receptionist triggers the view info method in an instance P of the patient info class and supplies the patient's identifier, or PID. P is the user interface object, which is displayed in the form as a form showing patient information. The instance of P calls the database to return the information required, supplying the receptionist identifier to allow for security checking. Database checks with an authorization system that the receptionist is actually authorized to perform the action, and if authorized, the patient information is returned and a form on the user screen is filled in. If the authorization fails, the receptionist is not authorized to perform this action, then we return an error message, and that's what the box with the alt shows us. Taking a look at another example, this one is figure 5.7 on page 134, and it's slightly more complicated. Note that the PRS stands for Patient Record System, and it's a system actor in spite of its stick figure logo, and we talked about that a little bit in the use case. So the receptionist logs on to the patient record system. There are two options available: transfer of updated patient information and the transfer of summary health data from the patient management system to the patient record system. In each case, the authorization system checks the receptionist's permissions. Personal information can be transferred directly from the user interface object to the patient record system. Alternatively, the database can create a summary record and transfer it to the patient record system. On completion of the transfer, the patient record system issues a status message and the user logs off. The third classification of models is structural models. So they displayed the organization of a system in terms of the components that make up the system and their relationship. They can either represent a static or a dynamic view of the system. And most of the time these take place in the form of class diagrams. And they're one of the most important types of structural models. So let's begin by looking at the class diagrams. So there are elements of class diagrams. They're used when developing object-oriented systems to show the classes in the system and the associations between them. So an association is a link between classes that indicates there's some relationship between the classes. When you develop models during the early stages of the software engineering process, objects represent something in the real world, such as a patient, prescription, or doctor. And that's, of course, one of the powers of object-oriented programming is that it makes a model of a real-world phenomenon. So we need the name of the class, the attributes and the operations, and then we need to describe the associations between the classes. So in order to determine if something is a class, you need to ask yourself 4 questions. Is this concept a container for data? Does it have separate attributes that will take on different values? Would it have many instances? And is it in the scope of the application domain? And this is an iterative task with object-oriented programming here. It's not just a one or done. And when you develop models during the early software development lifecycle, things typically represent something in the real world. As you get deeper into the development, you usually need to define additional objects that provide the required system functionality. So what are ways of going about discovering classes? And there are really 4 ways to do that. The first and probably the most common is the noun phrase approach. You have the written requirements or use cases or user stories. From there, you pick out the nouns from the written requirements. The common class pattern approach derives candidate classes from the classification theory of objects, and the use case approach picks out the classes from the use cases. This is similar to the noun phrase approach, and that one is categorized as a teaching approach and sometimes gets used in teaching. And last but not least is the CRC, or Class Responsibility Collaborator approach. Uses specially prepared cards that have 3 compartments. The class name is in the upper compartment, the responsibilities are in the left, and the collaborators are in the right. It ends up looking a bit like one of your Happy Kanban boards that you're doing in this year's Agile edition. And it's good from time to time, since it's possible to move the cards around and show the different links between them. And, of course, mixed approaches such as the noun phrase approach along with CRC are also possible. So there's no one size that fits all to class discovery. And this one, the CRC, is particularly popular with Agile. So here's a simple class diagram, and this is more of a traditional one. The boxes show only the class names and the association between them. Lines show the association and the cardinality of these associations. The star means many, so we can see that a patient attends 1-to-many consultations, and 1 to 4 doctors can run 1-to-many consultations. So that's the hospital doctor running 1 to 4 doctors running 1-to-many consultations. A patient can also suffer from 1-to-many conditions. This is 5.9 on page 136 of the 10th edition. In reality, classes have 3 compartments. The top part is the name, the middle parts are the attributes or member variables, and the bottom part contain the methods or functions. So let's take a look at 2 specific associations between classes. It's nice that the new text Malik covers in 151 covers a bit about class diagrams, so you've seen them before. Speaking of 151, remember that classes are the abstract form of a concept, while objects are concrete instances. For example, you could have a dog class and a Saguna object. Speaking of my dog, here a Saguna would be a particular instance of dog, or you could fill in your dog's name if you were building a class with your dog. So relationships, generalization is used for inheritance in object-oriented design, and it's represented by a hollow triangle on the relationship end to the connected classes. So a hospital doctor is a type of doctor. He or she has all the same attributes as a doctor, but also has a staff number and pager number, and would have probably visitation rights within the hospital and billing rights within the hospital, whereas a general practitioner might not have those things. They would have a practice and address. Aggregation or composition is a whole part relationship between a class and its components. The strong version is composition, and that implies an existence dependency. An object of a subset class cannot exist without being linked to an object of a superset class. So in composition, if you destroy the whole, you destroy the parts. For example, if you destroy your Somerville book, you destroy the chapters and the sections. In aggregation, the existence dependency doesn't exist. And Maciejczak, who was an author of a requirements analysis book, always said, if you destroy the crate that holds the beer, you didn't destroy the beer. And you can fill in your own jokes about Australians and beer here. So let's take a look at examples. And this is an aggregation example in our system. This is weak aggregation. If you destroy the patient record, you obviously don't destroy the patient. Likewise, if you destroy the patient record, the consultation still took place. This is figure 5.13 on page 139 of the 10th edition of the text. Putting it together, these can get quite complicated, and this is the Health Level 7 version 3 standard that models how modern health information supports workflows in healthcare settings. Here you can see the classes along with their names and attributes. You can also see the relationships and the multiplicities and generalizations there. In HL7 version 3, just to put it succinctly, this is an entire area of study that took me a year to get certified. You have entities that play roles that participate in acts. So I could be an entity, Keith, who is playing the role of a patient who participates in the act of having a health examination. This diagram also has colors associated with it. Green relates to the entities, yellow relates to the roles, blue relates to the participation, and red relates to the acts. Note that the language of communication is independent of all of these items, which is the one depicted in gray over in the lower left. Another example, and this one was taken from AFIT, or the Air Force Institute of Technology's lecture on UML. Here that we can see there are two types of sprites, both static and animated. Animated sprites are associated with states and can be either an enemy or a character, each of which has their own type of state. So those are associations, and you also see the generalizations there. And this one's probably more clear as a teaching example than the HL7. So behavioral models, these are the next class of models, and they're used to describe the overall behavior of the system. So again, there are two types mentioned in Somerville. One is data flow models that show how the data is processed as it moves through the system. And then there are state machine models that show the system's responses to events. These are good for real-time systems. You can also show behavior using sequence diagrams to a certain extent. So here's an example of a data flow model. And these were first introduced in the 1970s by Tom DeMarco as a way of illustrating the processing steps in the system. They're also useful because tracking and documenting how the data associated with a particular process as it moves through the system helps analysts and designers understand precisely what's going on. So, we develop these models and we talk about these models in order to implement them. Now, these come from 1970s. They don't have objects, but they are pretty common in business systems. And if you draw the messages from left to right, you can see the data processing that takes place in the system. This model shows the activity of an insulin pump system. Next are state machines. These are models. This model looks at the behavior of the system in response to external and internal events. They show the system's response to stimuli, so they're often used for modeling real-time systems, and they're a little more up-to-date than the previous one that we talked about, which was the data flow diagram. State machine models show system states as nodes and events as arcs between these nodes. When an event occurs, the system moves from one state to another. So for even more formal state chart methodologies, definitely check out David Harrell's on visual formalisms. That was 1998. It has a nice state chart of a digital watch, and I think we'll explore that probably in 461. State of the object is defined by its current values and attributes. The state chart, which is the states and the transitions between them, is life history of the object. You can attach a state chart to a class, and transitions are given in three parts. One is the event. What is it that happens, or what is the class responding to? The guard, which checks to see if the transition fire, and the action, which is the object's response to the event. So these are, again, good for event-driven systems. So here's an example of a microwave oven. Again, the blue dot is the start, and we move into the state of waiting where we display the time. If the full power is pressed, we move to the full power state, or if the half power state is pressed, we go to the half power state. There is a guard in here. No, I don't think this one actually has a guard. So, but it does show the states and the transitions between them. So, you might have a guard that indicates, hey, you can't open the door, while the microwave oven is in operation. There were some older models that prevented you from doing that. So here's a table with a list of states and stimuli for the microwave oven. The waiting state, half power, full power, setting the time, being disabled for safety, which is something that happens now when you open that door. Enabled, it's enabled, the interior oven light is on and display shows ready to cook, and then the oven is in operation. So again, what are the states and stimuli? The stimuli are the half power. That means the user has pressed the half power button. Full power, they press the full power button. Timer, door open, door close, start, cancel, and the user enters a number on a numeric key. Those are the different stimuli that can occur for our microwave oven. This is a Harel stopwatch that I was talking about from his On Formalism's paper. And basically, it's a neat bit of history. It's interesting to note the differences in the older diagram and the more modern one explored in the last two slides. Here, the outlines show different super states. And we'll finish up with a few words on model-driven engineering. And model-driven engineering is an approach to software development where models, rather than programs, are the principal outputs of the development process. Now, the dream is that code is generated automatically and it works. The pros are it allows the system to be considered at higher levels of abstraction, kind of like a visual programming environment. And generating code automatically means it's cheaper to adapt systems to new platforms. The cons are that models for abstraction are not necessarily right for implementation, and savings from generating the code may be outweighed by the cost of developing translators for the new platforms or fixing the problems that originate in the code. So different types of models: the computation independent model, model the important domain abstractions; platform independent model, models the operation of the system without reference to its implementation. So, you could do one for, a Java-based implementation, one for a C++-based implementation. It's usually described using UML that show the static system structure and how it responds to internal and external events. And then platform-specific ones are developed for different platforms. So, for example, you could develop it for a LAMP stack. And so in principle, the way that it works is you would develop your platform independent model, and then we could translate into either Java or C#. And so we can end up with both a Java and a C# implementation from the platform independent model, and they'll work and behave the same. Now, in reality, there is often a man behind the curtain. And sorry for the blurred capture. Executable UML is still pretty much a dream, but to quote Arwen from Lord of the Rings, it's a good dream. So that's the end. If you're interested in learning about other types of models, Cruikshank's book is quite good at discussing the ones used in the rational unified process. And I have a copy in my office if you'd like to take a look at it. Thanks so much for watching, and I know it's a longer presentation than I usually give, but I thank you for going through this because it's an important part of software engineering.